Hello students, welcome back. We completed up to section 2. Now let's go to section 3, functions defined by definite integrals. There are several ways to define a function through a definite integral, but here's the simplest and the most elementary method. Right here, the one I just highlighted in bold blue. And if you do that, you're going to end up with an antiderivative function. Basically, the definite integral is more or less an antiderivative. Not exactly the same, but more or less is an antiderivative. So the derivative of antiderivative, yeah, you're going to come back to the same thing again. Combining those two, you can re-express like this. The derivative of the integral is back to the original function. Just like the derivative of an antiderivative is the original, but there's a bit of a catch here. You see, we have f of t dt, now we have f of x. We have some character change. What's happening here? Well, in these expressions, character x is our main variable, and that goes right here on top of the integral. That's a variable. I'm highlighting the variable in red. And then here again. Now how about this t? This is a dummy variable. It doesn't do a thing. If you change to some other character, no change. Something else, no change. Whatever character, as long as that's neither x nor a, that's going to be okay. For instance, this is no. X is repeated again. We have an ambiguity. This entire expression is invalid. Same goes here. You cannot reuse a or x there, but anything else, no problem. Let's go back to t. Now the reason this is a dummy variable, well, that's because the computation itself was like that. Way back in section 2, you see, plug in x equals to b and x equals to a and subtract one from the other. So this expression here does not have any x in there anymore. You see, here, after calculating the antiderivative, plug in 1, plug in negative, subtract 1 from the other, so no more x. So whatever character I had, plug in 1 there and plug in negative 1 there and subtract 1 from the other will not change. So this variable here doesn't do a thing. That's why it is called dummy variable. It may be a bit politically incorrect term to call it dummy variable these days, but sorry about that. That term was invented more than 100 years ago. Here's an example. Calculate the given derivative, and we have the derivative of an integral. Let's take a bit bigger font so that you can easily see. Now, is it possible to calculate this integral and then calculate the derivative back again? Maybe, but it's unnecessary. Derivative and integral cancel each other out. We must have the same function back. But there's a catch. Not the dummy variable. We need the original variable x again. Of course, if this is z or u or something different, then those will have to change accordingly. That's one of the 3 things you have to be extra careful when we consider functions defined by definite integrals. Where's the variable and which is dummy variable? As you just saw, it's easy. Now that's one of the 3 things. Now let's go to the second thing. You see, the definite integral is more or less an antiderivative, but they're not exactly the same. The location of x can be affected. The location of x can affect the outcome. If you switch x and a, for instance, as you can see here, let's look at it in a little bit bigger font. What did I do? X to a. If you switch these two, then the negative of a to x. So in the end, we get the negative of the original function. Remember this? If we switch the top and bottom, we are putting the negative sign. It's one of the properties of the definite integral. Integral from a to b f of x dx is negative of integral from b to a f of x dx and vice versa. Another way to see the same thing is to go back to the fundamental theorem. Capital F of b minus capital F of a versus capital F of a minus capital F of b. If we switch a and b, no wonder we get the negative of the original. Either way, you can see that switching top and bottom will give you negative. So that's the second thing that you have to be concerned. Well, let's go back to the second problem here. And again, let's take a little bit bigger font. It's a derivative of the integral, so we have to have the same function back. And then my variable is x, so we have to have x in place of u, but that's not enough. We have to switch to an x, so we have negative of this. Or maybe I should write an extra step here. Changes to 2 to x, and then that results in negative, like this. So that's the second thing that you have to be concerned. Number one, proper character, proper variable, putting x in there. Or if this problem had been given by not x, but something different, say, for example, let me change this into, say, w, 1 to w, and then w like that, then all these should be w's. Doesn't have to be x. Whoa, this should not be w, this should be y. And that go with the dummy variable. And instead of y, if I change to something else like u already see it down there, so let's choose something else. S, you see? So, what's the variable? What's the dummy variable? Remember that? And then also, the location of the main variable, top or bottom. Remember that. Those two. Now, let's go to the third thing that you have to be concerned when you consider functions defined by definite integrals. And this one is much harder. Here's a theorem. Combining the chain rule and the fundamental theorem of calculus, we get this theorem. The derivative of the integral, and this time, both a and b are functions. And then the fundamental theorem applies, plug in the top and plug in the bottom, subtract one from the other, but also by chain rule, the derivative of the inside pops up. Now, one of the common mistakes here is to take the derivative of this integrand. No, don't do that. Derivative and integral cancel each other out, so no further derivative. So this f must stay the same. In fact, the best way to understand it probably is to prove it. So let's try that. If you can't follow the proof at all, then okay, you can give up and come back to this and use it as a formula, but At least let's try that. Here's a sketch. By the fundamental theorem of calculus, there is an antiderivative function, capital F, which we don't know, and then you can plug in the top and plug in the bottom and subtract one from the other. The fundamental theorem, nothing more. Just remember, a of x and b of x are functions. Now here, take the derivative. Then, this is a composite function, and that too is a composite function, so the chain rule applies. The derivative of the outer function, capital F, becomes the original function, small f. And then, step 2, inside doesn't change, so b of x stays. Finally, step 3, the derivative of the inside, b prime, you multiply that. Do the same thing here. That's how you get the right-hand side. Again, do not take another derivative. You see, this f of t and take another derivative from there is one of the common mistakes I see. But don't do that, because the derivative and integral already cancel each other out. So just plugging in and plugging in, that's how the fundamental theorem works. How about this derivative and that derivative? Those are coming from the chain rule. So that's different. Let's look at an example associated to this. And here's a good problem right here. Let's copy and paste it here. And I'll be bigger font. Okay, all right. And then this is my B. And this is my A. Okay. First, just plugging in. So copy and paste this thing here. And then in place of t, I have to plug in x squared plus 2x. That goes inside. There, and then there. So we are up to here. And then we have to multiply the derivative of the inside. What's the derivative of this x squared plus 2x? 2x plus 2. Again, let's highlight it in blue because it came from B. Did I complete the first term? Please check. Okay, let's do the same thing here. Do not take the derivative of the sign. Derivative and integral already cancel each other out, so you have to get the same integrand back. Copy and paste. And then in place of the t, I have to substitute this 2x minus 1. It's so hard to do that. Let's just type it in. 2x minus 1. And then we have to multiply the derivative of the inside. That's just 2, isn't it? Let's put some space in between. I guess that completes the problem. Copy and paste, substitute top, derivative. Copy and paste, substitute the bottom and the derivative. That's the most general case. And in a special case, if one of them is constant, then you're going to get 0 there or 0 there. So this case will cover the previous cases too as the most general situation.